Hello friends, welcome to our channel. Let's have a look at problem 3695. Maximize alternating sum using swaps. This problem is marked hard by leetcode. However, the logic is rather straightforward. Here, the method or the abstract data type we are going to use to solve this problem is union find or disjoint set, if you speak from the perspective of data type. So the idea actually is decomposition, right? So this idea is actually very common in CS and in mathematics. So here, what we want to do is to compute the sum of even indices minus the sum of odd indices. And also we are given a swap list, which gives the indices where you can swap the corresponding elements any number of times. So what we want to do is to return the maximum possible alternating sum of the given list, right? So you can analyze the example 1 following the explanation, but we are not going to go into details there. So let's look at the constraints, right? First, the list can be as long as 10 to the power 5. Therefore, we need to pay attention to time complexity of our solution. And those are some consistency evaluations, right? Like including this one. And also the numbers are positive. So with that said, I guess we are ready to do the implementation. So here, actually, if you want to implement union find, so there are two options. So one is implement it as a class, a separate class, or implement inside the solution class here. I'm going to use this one. This option in this video. But we have a playlist for union find which contains more than 20 problems at least, right? So you're welcome to look at all the different use cases there corresponding to different leetcode problems, right? So this is one thing. So another thing I want to mention is that there are two methods, two main methods we're going to implement. One is find, and one is union, right? So also when we implement find, so we can use path compression if you like. And when we implement union, we can use union by rack. So these two tricks actually accelerate the method, right? So in other words, overall improve time complexity. So this is just some comments. So after that, once you do the union find with this swaps, you can get connected components, or you can call it clusters, right? So those connected components or cluster corresponds to different subsequences of the original array, right? So now let me explain what's the logic. So here, this is what we want to compute: the sum and even indices minus sum and odd indices. But we know that the sum and odd indices will be the total sum minus the sum and even indices, right? If we do some simple algebra, you will see this will be 2 times the sum and even indices, so minus the whole list, right? Therefore, if we want to do the problem, so we just need to know. So for those swap subsequence which can do swap, so we put the largest numbers corresponding to the indices to even indices, right? So that's the same. So this formula, so if we compute for the whole list, so if we partition the list into disjoint subsequence, right, then this still holds, right? So that's actually what we are going to do. This partition is the main idea. So now let me give an implementation. So first, I'm going to get the length of nums, right? So if you look at here, pi and qi is greater than or equal to 0, and less than or equal to the length minus 1. In other words, they are indices, right? So the first step will be implement union find. So we can have roots. So we can do like this. The roots first set to be themselves for I in range n, right? And then the regs. So I'm going to set it to be 1 for I in range n. So this is the initialization. So next, what we want to do is we want to find method. Given the index, we want to find its root or its ancestor. Then also we define a union method. So given two indices, so we want to find the union, the corresponding cluster, right? And then what we are going to do is for the pairs, for say ij in swaps, so we are going to do union ij. So this way we are going to get the clusters, right? And then we do this computation here. So once you separate into steps, so the overall logical structure will be very clear. So now let me first do this. So here result, I'm going to set to be I. So basically it's a while loop. While result does not equal to roots result. And then I'm going to set result to be roots result. So once we exit this while loop, then this condition will be not valid. In other words, result will be the same as result root. So this is what we want to return. So typically, this is the vanilla implementation. But if we want to use path compression, so we can do something like this. So in other words, we apply this, we set the roots of the result to be the roots of the result. It's like apply this roots to this below line in both the right and left side. So this is the so-called path compression, right? So in some problems, you don't need this trick. It can do just a vanilla implementation. But here, let's use it. So now let's look at union by find, union with by reg. So first we get I root and j root. So because we have implemented the find, so we can do find I and find j, right? So first we check if I root equal to j root, means they are the same cluster. We don't need to do any operation. If not, right? So we can combine or union the two parts. So we can do the union based on directly you set the root of say this guy to be this I root, that will be 8. However, we want to accelerate a little bit, so we can use union with reg. So first, if regs root I root is greater than or equal to that of j root. In other words, the j root corresponds to a smaller cluster. So we can add the smallest cluster to the larger one. So what we do is roots of j root equals I root. And then we increment the reg of I root by that of regs of j root, right? So otherwise, so we do the reverse. Roots, we set I root, the root to be j root. And then the regs, we also do the same thing, but we do this, right, in the reverse direction. And that will be 8, actually. So here, because we want to find the corresponding clusters, we can do 1, right? So define get clusters. So we can use collections default dict. So we provide a container or callable that I use as set. So you can use list as you like. So then basically what we do for say I and let's see root, right? So this roots. So for I and let's see, so do I need to use the root? So I, so we can do this for I in roots. So we can find the roots. So find I, and then what we do is dr union equals, so because it's a set, right? Union with respect to r, or you can just say d at this I. So then you just return this d. So that's basically the two main function. We finished the implementation of the unified. This is the hyperfunction, right? So now let's look at the problem logic. So this here is problem logic. Let's first do this one and look at the clusters, right? So we can do clusters equals get clusters. So we can do a print for the clusters. Clusters, right? So you see, for this one, because 0, 2, and 1, 2 can swap, so you actually correspond to one whole thing, that is 0, 1, 2. And for example 2, so 1, 2 is a cluster, and 0 is another one. So you see 0 is another one, and 1, 2 is another one. And for the third one, so there's no swaps, so you get a 3 cluster. Well, let's see, the length is 4, you get a 4, right? Let's see, 1, 2, 3, 4, 5, 6. The length is 6, right? 0, 1, 2, it's isolated, right? So then we can follow the hint, right? So you get the connected component, and then we get the number of even indices for each one, right? Then do the sum. So I can do. So here we compute or prepare the return, right? So what we are going to do is this. So for each cluster, so we get the count of the even indices, and then we compute this this part. So sum at even indices, right? And then we just compute all, and then we multiply by 2, and finally we just minus the whole sum of the list in one go, right? So how do we do this? So see sum at even indices. So we set it to be 0, right? Then for clusters, for cluster in clusters, right? So here we got this, and then we get the count of the even indices, right? So we can first use a list comprehension. So we can do this. Let's see. The list comprehension, let's use a temp. So we can get, say, nums. So is it nums? Yes. So nums I for I in cluster, right? So we get this, and then so we are going to sort it, right? Sort see, I just use reverse equals true, right? And then we also get the count of the even indices, right? So even indices. So let's see, count equals sum. We can write so I, so 1 for I in cluster if I modulo 2 equals 0, right? So then we are going to set the largest numbers to this count, right? So basically what we do corresponds to sum at even indices. So it's incremented by sum of temp at this, right? And then this way, if you do for all the clusters, you will get the sum for indices for all the list after swaps. And then what you want to do is just return the 2 times sum at even indices minus some nums. So that's the full code for this problem. Let me first do a run. Integer object is int object is not iterable. For I in cluster, let's see. Sum, see 1 for I in cluster. If let's see, count. Let me first do a print. So cluster. Let's see. Integer object is not iterable. So here for I, 1 for I in cluster. So count. So here we have this one. Let me first comment out this one. Let me do a test to print out a cluster. So integer, so temp 185. So not temp nums I for I in cluster. Let me see what's the problem. So int is not iterable. So here nums for I in cluster. So let me. Oh, so here I guess I write. So this should be the values, right? So now let's comment out these 2 lines. Now let's see. Yeah, it passes the 3 test cases. Now let's look at the generic case. Yeah, it passes all the cases. So let me delete this print and then do it again. Yeah, so that's basically about it for this coding part. Here, let me make some comments. So first, I guess, most important thing for this problem is this decomposition idea. So once you realize this, actually the computation is rather straightforward. That's the one thing. Another thing is that you should have a certain level of familiarity with unified or disjoint set. So actually, if you look at the playlist in my channel, you'll see it contains more than 20 problems. I had practiced quite a lot. Therefore, I can directly write the code without preparation for passing or accepting for this leetcode. However, here, so when you get the clusters, so here what you get actually is a dictionary, right? So the clusters corresponding to the values, and the key can be understood as the name or tag of the cluster, right? So this is the second comment. The third comment is some details in the implementation. So in this implementation, we used path compression, and here also we used so those is union by rack, right? So if you don't use this tool, actually the find and the union method can be can be implemented just one line here, or also one line here, right? You replace this by one line. You just need to set, for example, roots of I root equals j root. That's it. And here you just write one line to, for example, you can write say return result I if result let's see return I if roots I equals I, else what you return? You return find roots I, and just also one line, right? So, but here what we implement actually invoke these 2 tricks. One is path compression, and one is union find. So actually, this problem is provides a good problem for practicing union find. So with this comment finished, I guess that's it for the current video. You're welcome to follow up in my YouTube channel and practice those problems or invoke some discussions. With that said, thank you for watching.